Hello, everybody, and welcome to lesson 4.6 about optimization. Optimization is basically the process of trying to make something as efficient as possible. So let's get cooking today talking about optimization. So like I said, optimization is basically the idea of making something as efficient as possible. You guys as students are familiar with the idea of optimization because, for example, you guys like to optimize your grades by trying to get the best grades possible with as little effort as possible. So this concept is actually plays into the idea of optimization. So for example, if I want a rectangular enclosure is being built with 400 feet of fencing, what dimensions would maximize the area? So basically what I want to think about is area is equal to length times width, right? And then I know that this 400 feet is going to be the perimeter. Perimeter equals 2L plus 2W. And more specifically, the perimeter is going to be equal to 400. So I want 400 to be equal to 2L plus 2. Why did I write a 4 right there? That should be a W. That's not even close to a W. 2L plus 2W. All right, so the idea here is I want to maximize the area. In order to maximize the area, I can take the derivative of this area function and figure out when it's equal to 0, because when the derivative is equal to 0, there's a possibility of a critical point on the graph. So what I'm going to do is, right now this is area equals length times width. What I want is I want this in terms of just one variable. So when I take the derivative, it's in terms of just one variable, and I can figure out either the length or width that would maximize the area. And then from there, I can use that to use this equation to find the other quantity. So I'm going to solve this for L. So length would be equal to 400 minus 2W over 2, which would be equal to 200 minus W. So now I'm going to go over here to the area formula. So area is equal to 200 minus W times W, which is equal to 200 W minus W squared. So now if I find the derivative of the area with respect to the width, this would be 200 minus 2W, and I notice this is equal to 0 when the width is equal to 100. So if the width is equal to 100, then this is going to be 200. The length will also be equal to 100. The only other thing that I would want to verify is I would want to take this derivative function right here and verify that this is actually a maximum and not a minimum or an inflection point. So if I think about this derivative right here, if I plug in something larger than 100, the derivative will be negative. If I plug in something smaller than 100, the derivative will be positive, which means this is a maximum, which means this area is optimized when the width is 100 and the length is 100. So with rectangles, this is actually fairly intuitive because you probably learned during geometry to maximize the area of a rectangle, make it a square. So this makes sense that this worked out to be a square, and that will be the maximum area. So in general, when you're solving optimization problems, you want to read the problem carefully, draw a picture if you need to. So if possible, or if necessary, draw a picture. It's helpful to label small parts as single variables so that you can avoid fractions. So then the major part is you want to write a primary equation for the quantity to be optimized. So right here, the first thing we did is write an equation for area. And then you want to identify the limiting factor or the constraint, write a secondary equation. So in this case, the perimeter was the limiting factor, and I used that to write a second equation. All right, so we're going to solve the secondary equation for a variable and then substitute back in the original function, which is what we did here. We solved for length and substituted into the area equation. All right, and then you're going to simplify that equation and then take the derivative and find any critical values. And then you're going to determine the absolute extrema using one of 3 methods. And we'll go over those methods at the end because we've actually kind of done this before of curve sketching. But then we're going to answer the question in complete sentence using appropriate units. I didn't write all of that out here because I ran out of space. But here I would say the dimensions to maximize the area of the enclosure would be a width of 100 feet and a length of 100 feet. And then you're going to smile and have a great time because optimization is a blast. All right, so here's another example. This is a small example. The sum of 2 positive numbers is 8. What are the 2 numbers that will have the largest product? So I notice largest product. What I'm trying to optimize is the product of these 2 numbers. So I'm going to call those numbers A and B. So I want A times B to be equal to P, whatever the product is. All right, and then I know the sum of those numbers is 8. So I know that A plus B is equal to P. And P in this case, or sorry, not P. A plus B is equal to 8. Sorry, P stands for product in this case. So A plus B is equal to 8. So again, this is what I want to optimize. This is my limiting factor. So I'm going to solve this for one of the variables. So I've got B equals 8 minus A. So now I'm going to take that and substitute back into the product formula. All right, so I'm going to substitute in here, and then I'm going to differentiate this. This is A times 8 minus A equals P. And now we're going to take dP over dA. All right, and if we simplify this, this would be 8A minus A squared. So this derivative would be 8 minus 2A. All right. So this is 8 minus 2A. So I want to figure out when this is equal to 0. So 8 minus 2A is equal to 0. So I'm going to subtract 8, divide by 4. So A equals 4. So if A is equal to 4, then B would also be equal to 4. But I also want to just check and verify that 4 is a relative maximum and not a minimum. So if I look at the derivative right here, if I plug in any value greater than 4, this derivative is negative. If I plug in anything less than 4, this derivative is positive, which means this function will increase and then decrease. So 4 is a relative maximum. So this would be my answer. So the same kind of concept applies here. The product of two positive real numbers is 7. What value would you maximize? What values would maximize the sum of the two numbers? So the product of the two numbers is 7. So, and I want to maximize the sum. So I'm going to write an equation for the sum. A plus B equals S. The product is 7. AB equals 7. And I'm going to leave the rest up to you to do. But the idea here is, again, I want to differentiate this equation after solving for one of these two variables using the limiting factor. So I talked about verifying relative extrema, and if you notice, we've already verified a couple relative extrema, but I'm going to give you the words for the 3 methods. So the first one is biggest value. So what you can do, this only works if you have a closed interval. And actually in this case, we had a closed interval between 0 and 7 because this is positive real numbers. Here we had a closed interval. Actually, sorry, no, we did not have a closed interval here because any positive real number, there could be any 2 positive real numbers that multiply to 7. Here we did have a closed interval from 0 to 8 because the sum of 2 positive numbers is 8. If I take any positive number greater than 8, the second number would have to be negative. So I had a closed interval here, and I also had a closed interval here because I maximized at 400 feet. So if you have a closed interval, what you can do is you can use the endpoints and any critical values in between. Whichever one has the largest y value will be the maximum. Whichever one has the smallest y value would be the minimum. Method 2 is the first derivative test. And this is actually the one that I tend to use the most often because in most of these cases, we're taking the derivative anyway, so we utilize it. And that is what we did here when we said, hey, if I plug in something less than 4, then I get positive. I get if I plug in something greater than 4, I get negative. So based on the behavior of this function, this must be a relative maximum. So that's the idea behind the first derivative test. Basically, I take my critical values and I find if the derivative is positive or negative on either side of them, and that'll tell me about whether they are what kind of critical points are relative maximums, minimums, or neither. So the third one is the second derivative test for absolute extrema. And this one I don't use very often because typically when we're looking for minimums and maximums, we will have the first derivative, but the second derivative test can tell me a little bit more about what this function does in terms of graphically, but for optimization, I don't tend to use it very often. But if you decide to use it, what this is doing is instead of finding values to the left and right of your critical values, you're going to think about the value of the second derivative around your critical value. So around your critical value, if the second derivative is positive, which remember from curve sketching, that means it's concave up. If the second derivative is positive around your critical value, then that value will be an absolute minimum. If the second derivative is negative around your critical value, then that's going to be an absolute maximum. And what it actually doesn't say here is if at your critical value you change concavity, then your critical value actually is not a relative maximum or minimum. It's an inflection point. So that is it for today. Today was about optimization. And then at the end, we reviewed verifying relative extrema as part of optimization. So I hope you took some good notes. I hope you come to class ready to learn. And I hope you have a fantastic day. I'll see you in the next video.